in 2005, and after that, we also expanded it to ancillary service market, and then later on we had a source integration, and now there are a lot of interesting market development and new research aiming towards the future resource integration. So these slides basically summarize some of the important market development since we started. So I want to share some past development and some of the future design challenges. Here, this one basically is to summarize our early stage. So we first, people actually started to discuss about forming MISO in 1996. That was after the FERC order, around that time, had the FERC order 888 to build this RTO, like some kind of centralized neutral entity to facilitate the market, establish the competition. And then, so it took quite a while, until 2005 we first started the market operation. But at that time we only have the energy only market. So we have like 26 local balancing authority. When we clear the market, we send them the energy dispatch and the NSI, net schedule interchange to each LBA, but they will run their own AGC and then carry the operating reserve on their own. But later on, we consolidated all these control area into one single balancing authority. So the ancillary service market was launched in 2009. So here is basically the function. In 2001, we were approved as the first RTO by FERC as a reliability coordinator, doing this congestion management, to basically administrate all the transmission lines in the footprint. And then in 2005, start energy market, that included the day-ahead, real-time, and FTR market. And then 2009, after we consolidated those local balancing authority, then so the significant benefit. So you can see, like for the regulating reserve, before we consolidate the LBA, those local balancing authority, they each carry their own regulating reserve and the contingency reserves. So the total regulating reserve was about 1,159 megawatt, but post SM we only carry about 400 megawatt. So we have been carrying that amount of regulation even after the South region joined. So the South region, include about 30%, added about 30% of the total load. And then for spinning reserve, and then before that, each area they need to be prepared. They carry continuing reserve to prepare for the largest the generation event. But even back then, they have some kind of a reserve sharing group. The several LBA they will group together trying to share contingency reserves to reduce the total amount of spinning and supplementary reserve. But after we consolidated, the whole region just need to be prepared for this largest event. So the spinning reserve reduced from 1,400 megawatt to 935 megawatt. So of course, with co-optimize of energy and the reserve, it brought a lot of benefits. So the highlight of the MISO day-ahead real-time system. So we have co-optimized energy and regulating reserve and contingency reserves. And recently we also introduced the ramp product. So those are all optimized in both the day-ahead and the real-time market. And in day-ahead market, we actually have a good participation. So 99% of the resource are committed in day-ahead market. And then in real-time market, it included the reliability assessment commitment, we call it forward rack. And then that was run after day-ahead market close. And then because day-ahead market is all based on the offers and the bids. And then so in the forward rack market, we use medium-term load forecast to evaluate, whether we need to commit additional generator. And then throughout the operating day, the intraday rack is run every hour, and then look ahead commitment is running every 15 minutes. Then we get into real-time economic dispatch. It is run every 5 minutes. So and in addition, we also have a lot of long lead generator. So the operations also run 7-day forward rack. Those are aimed to commit to these slow start long lead generators. And then the exposed pricing process actually is basically after we finish the commitment and dispatch, there's a pricing run. So MISO actually is leading in this area to develop the efficient price. So most of you probably know the LMP-based market. The LMP actually only reflects the marginal cost, but there are a lot of generators with significant fixed cost. Especially for this quick start CT, a lot of them are block loaded, and then those generators in the past cannot set price. And then so MISO actually developed this called convex hull pricing method. We also call it extended LNP. So that actually can incorporate the fixed cost into the pricing, so that can give much more efficient pricing outcome. And then after this commitment, dispatch, and pricing, the settlement system is a two-market settlement. So we have day-ahead settlement is based on the day-ahead ELMP and the reserve pricing, and then in day-ahead congestion can be hedged against the FTR, and then so even though we have the extended LMP, but in the end the pricing may not be able to cover the total cost, and then that's by nature the non-convexity of the problem. So there's a revenue sufficiency guarantee. So if a generator cleared and the price cannot cover their total cost, then RTO will make them whole. Make sure they don't end up with losing profit. And then in real-time settlement is based on the real-time LMP and the reserve, MCPs for the reserve product. And then but real-time settlement is only on the difference, so the delta between day-ahead and the real-time. And also we also have this called price volatility make whole payment. So it's similar to the revenue sufficiency guarantee. So if a generator follow MISO instruction but end up with losing profit, and then MISO will make them whole. So that's an overview of the the market structure. And then here is a diagram to show the uncertainty management. But really, in operations, the operators actually they need to manage the uncertainty all the time. So the goal is in the end, when you get into that operating target, we'll have enough balance. So this process actually is a multi-stage process. So it started with the 7-day rack, and then into the day-ahead market, and then intraday rack, look-ahead commitment, and real-time scale. And then even though real-time scale is run every 5 minutes, there's a still gap between that and the actual system condition. So those gaps are actually, we intended to use the operating reserves to bridge the gap. Like a regulating reserve is deployed every 4 seconds, and then spinning and supplemental reserve are prepared for the contingency event. And then, but along the process, the further away you have a more uncertainty. So those uncertainty, operations, they use some kind of additional, for example, headroom. When they clear the forward rack or 7-day rack, they know the input data are not perfect. There's some, they do some historical analysis trying to figure out the inaccuracy in the forecast, and then they put additional headroom to prepare to account for these uncertainties. And here is a summary of all the market product and all the market resource, because different resource may have different kind of characteristics. Like generator, normally it can provide all the service. So we have the energy regulating reserve, spinning reserve, and supplemental reserve. And I recently introduced the ramp product. And then we also have a capacity market. It's also started relatively recent. So this is capacity market is aimed towards the normally it's for the peak load. Make sure there's enough generator resource in the system to meet the peak demand. If not, the market should give a signal to attract new entry. Like people may build a new generator or introduce new different types of other resource. So for generator, normally it can provide all these service. But then there's this DRR is basically demand response resource. We have two types, DR type 1 and 2. The type 1 is basically can only be on and off, and then DR type 2 can actually be dispatched. We actually have some like a Alcoa alumina plant. It's a load. There's some room for it can follow 4-second instructions, so it has been providing regulating reserve for a long time. And then so we also introduced the stored energy resource, the SER. So those are for short duration storage. So it can only provide the regulating reserve. And then the SER2. So recently, there's some new storage technology. It's with kind of a medium duration, like for some are longer than 4 hours. So we introduced this SER2 so that it can provide all the service. And recently, there's a FERC order 841 require all the RTUs to provide, to allow the energy storage to provide all the services. So we're going to probably change the SER2 to a new resource called energy storage resource for the FERC compliance. And then there are also some other like EAR is really for some HVDC, the hydros. It's sending through HVDC to MISO from Manitoba Hydro. And then the DIR, so the EAR is basically like a dispatchable dynamic schedule. And then DIR is basically dispatchable intermittent resource. Those are created for renewable, like we had a lot of wind penetration. And then in the past, it's very difficult for operations to handle these renewables. So this DIR was introduced. Basically, it will use the wind forecast as the maximum limit and then we can dispatch the wind between 0 and its maximum limit. And then wind can also submit the offer. So normally they will offer negative price because of the tax credit, and then normally it's around negative 30. And then if they are causing congestion, or if the system has a over generation issue, then those DIR can be dispatched down, and then that when that happens, we will see negative L1P. So those actually are much efficient way to dispatch those renewable resource. And then of course there's some other services are currently not included in the market. For example, the reactive power supply and the voltage control, and the black start service, and also primary frequency response. And we have some interesting discussion about whether we need to introduce the new product for the primary frequency response capability. But so far we haven't seen the need, so it's still under discussion. So here these few slides is about the past development on energy and the ASM. So I mentioned earlier, when we initially started the ASM market, we have the regulation spinning and supplemental reserve. So we had some very interesting experience even during the ASM development on how to formulate the ramp constraint, and so there are different ways you can require the ramp to support all the product, right? On 5-minute basis, when you clear energy regulating reserve and spinning reserve, we can formulate it mathematically, saying the ramp need to be to support all these products. So this is a very tight constraint, and then it actually in the end causes a lot of shortage, because sometimes participants, they don't offer all their ramping capability, and then in the end we don't have enough ramp to support the clearing of all the product, but it's not a good outcome, because in the end, if we have regulating or spinning reserve shortage, then we will not have enough for the AGC and contingency reserve deployment. So in the end, we have to relax those constraints. So we have some paper, if you're interested, you can search for that. So with that experience, actually later on it actually inspired us to develop this new ramp product. I'm going to discuss it later. And then another interesting thing is on this reserve deliverability. So really, when we clear reserve, we need to make sure it's cleared in the right location, and otherwise, when we need them, it may not be deliverable. So, so we have some kind of interesting production scenario, and then later on we developed some new constraints to address those deliverability issue. So when we first started, we took this traditional way to define the reserve zone, and then using offline study to basically calculate the zonal requirement, and so that one actually it doesn't really work very well, because in the offline study it's very difficult to kind of match what's happening in real time. So we had a historical scenario. The offline study, when they did the study, everything is okay. There's no zonal requirement come out of the study. But when it gets into the real time, so when in some area when we have a lot of wind in the north region, when the wind is heavy, it's causing congestion. Then we dispatch the generator down right in that region. So when the generator in that region is dispatched down, it leaves room to clear reserve. So about 70% of the spinning reserve are cleared in those kind of congested area. But of course, if any event happen, if we want to deploy the spinning, it's not really going to be deliverable because it will cause more congestion. So that actually make the operations very nervous. And then there's another instance is happened recently. Is basically the study actually identified the zonal issue. There's some import limit. So they actually calculated some spin reserve requirement in a zone. But the problem is if you don't optimize that with energy, so what happened in production is in order to clear spinning in that zone, it's actually back down energy. When energy is back down, then the import flow, pre-contingency flow increased. So in the end, the post-contingency flow it doesn't really improve because the spin deployment just offset the pre-contingency increase. And then for a few days, the zonal price was really high. It's even close to the $1,000 kind of a shortage price. But really, the spin cleared. First of all, that zone doesn't have enough spin. That's why we have the shortage. And then, but even if it's cleared, it really didn't help the post-contingency flow at all. So we did this study, and in the end, the operations and participants, realized that without optimize those reserve product, the energy and the reserve, it's not going to produce the reliable and efficient outcome. So what we end up with is we actually introduced some constraint explicitly in the optimization to address the deliverability issue. Basically, traditionally, in the market operation model, we only have the flow from energy component, right? So the energy redispatch will, we formulate the energy redispatch, the impact on the flow. So in order to consider reserve, we actually introduce a new set of constraints. We call it the post-deployment transmission constraint. So the left-hand side of the constraint include, not only the flow from energy, but also the flow from the reserve deployment. So we have a set of constraints to formulate the flow from regulation reserve deployment up and down, and then also a set of constraints to formulate the largest event from each zone. So if we have a largest generated trip in zone 1, and followed by a spinning reserve or supplemental reserve deployment, and then we need to make sure the flow will still be within limit. So those constraints actually greatly improve the reliable and efficient operation in real time. Those constraints are enforced in both day ahead and every 5 minutes dispatch. So it gives a lot of transparency to the operators. So those are about reserve deliverability. And then with the more and more penetration of renewable, we expect to see more kind of dependence on the reserves, like this new ramp product. And we're also in the process of evaluating the 30-minute reserve product. So for all those reserve products, there's a deliverability issue. So those set of constraints are actually intended to be applied to all these reserve products. But of course, if we add all of them, it will introduce a lot of computational challenges. So those are some interesting problems to research. And then for the flexibility, so I mentioned earlier, So during ASM, we see the challenging of managing the ramping capability. And then even before that, when we have the energy only market, we have two market system, right? So in that head, we clear on the energy schedule on an hourly basis, and then when we first started the market, a lot of participants, they are actually very nervous about we moving them around. So they actually they want to lock their real time to their position. So that caused a lot of problems for real time operations. So that's why we introduced this price volatility make whole payment. Basically, saying if you follow MISO instruction and then end up with losing profits, then MISO will make you whole. So that actually helped to address some of this issue. And then after, when we first started the market, we only have 500 megawatt wind. But then in 2015, it's about 15,000 megawatts. So it's increasing, penetration is very quick. And so we also anticipate to see more solar in the future. And then those renewables introduce this kind of uncertainty, right? So we all know they're intermittent. But after we introduced the dispatchable intermittent resource, that helped greatly. But still, this resource can introduce uncertainties in the dispatch horizon. So that's why we actually probably skip this. So we actually started the discussion about a new product called the ramp product. So this ramp product basically is during our real-time dispatch, we'll make sure there's enough ramping capability for the resource. Basically pre-position a resource to make sure there's enough ramping capability to accommodate the variation in the net load. So here, the ramp product requirement actually is determined based on the forecast and historical forecast error. So those are adapted, calculated in real time, in their head and real time based on the forecast and the historical error. The RAM product actually greatly improve the management, or the optimal use of the ramping capability. So it's otherwise in the past, because in real time we do single interval dispatch. If we don't pre-position, when there's like a sharp load change, then normally there's not enough ramping capability to meet that load change, and then we often run into the resource scarcity. But with this RAM product, those scarcity are actually reduced, a lot. And then, so I'm actually already touched the dispatchable intermittent resource. So this is basically, allow us to dispatch down the wind, when needed. So most of the time they will be at the maximum, because they have this tax credit. But sometimes they may cause congestion, or some during the wind season, at midnight we could have over generation, and then but allowing dispatch wind down, it actually bring a lot of efficiency and also improve the reliability. And then here, this few slides is about the price formation. So I mentioned earlier, MISO actually is leading in this area on the development of the convex hull pricing, and you call it extended LMP. And all these market development projects actually, when you bring this, incorporate this service and the product into the market optimization, the price the pricing will reflect the value of those services. So those in general will all help improve the efficiency of the price. And but for the ELMP specifically is to address this fixed lumpiness, fixed load. So that like this diagram shows this red lines show the total cost function. So basically, if you commit a generator, there's a fixed cost, and then the total cost increase, but the marginal cost does not necessarily increase. And then this introduce price inefficiency. Basically, when you commit an expensive CT, the total cost increased, but the price may drop. The LMP price may drop. And then the convex hull pricing is basically this blue line. It's trying to form this convex hull so that the derivative of this cost function, will always increase with the total cost. And so with the introduction of this ELMP, we can send the efficient price signal. When we commit an expensive CT, then the price will reflect the better reflect the total cost. So all the generator or the resource should have the incentive to follow the instruction. And then this diagram is basically about the emergency pricing. So what happened is similar kind of situation. What happened in the past is when a MISO declare emergency, we could call on a lot of demand response, called LMR, so load modifying resource. So when these resource basically when the load is curtailed, then the price actually will drop, right? So it didn't really reflect the system condition. So when we are in emergency, we expect to see higher price, to encourage voluntary curtail of load. And then, so this emergency pricing is basically building this logic, in the pricing run, basically to make sure the price after emergency is not lower than the price before emergency. So these are kind of this price curve, the supply curve. Basically, if there's an emergency declared, we curtail load, or we commit emergency resource, the supply curve actually will shift, causing price depress. But then this emergency pricing logic will make sure, the supply curve on the supply curve, the price is not depressed, after declare emergency. So those become more and more important because for many years we never had this, we never called this emergency resource. But recently we actually had more and more this emergency event. So recently there are a lot of exciting developments, like new emerging technology. So we actually worked on several projects to incorporate non-traditional resource like storage or demand response and distributed energy resource. But it also introduced a lot of challenging because these resources, a lot of them are small and they need aggregation. And then, so that actually introduced a lot of problem, on locational marginal pricing based market has a lot of advantage in the consistency between the pricing and dispatch. But if we allow the aggregation, and then it will introduce very challenging to the congestion management. But if we don't allow aggregation, then it can potentially introduce a lot of small resource and causing computational difficulty. So those are the problems we are currently studying, and then so there's still no kind of ideal solution for this problem. And then, so actually the next few slides really was intended to introduce some of the research in the computational area, but looks like we're almost run out of time. So maybe I'll just have some highlights. So these few slides really is about the market clearing system. Is basically including the optimization and the network application, the iteration between these two. And these slides actually come from Groovy. So at one point we had a lot of difficulty in solving day-ahead unit commitment, and then so they actually show these slides to basically give a sense of how large the unit commitment problem in the day-ahead market. So you can see the problem size is actually really pretty large, though, compared to all these other problems. This one basically show all the problem size Groovy has, in their customers. And so this market clearing problem is very large, and then so from very beginning, MISO has been putting a lot of effort on improving the computational performance. So when we first started, we need 6 hours to clear market, and then on-time posting is only about 87%. But over the years, we greatly improved the performance and reduced the clearing window. So currently, it's about 3-hour clearing window, and with about over 99% on-time posting. So we put a lot of emphasis on research in this area, and so of course, in the future, the problem can become more and more challenging. With large penetration of potentially the future resource like DER or storage in small distributed resource. And also the interaction between transmission and distribution. So that could currently most of the clearing software are DC OPF based model, and then you could potentially need to consider more and more of these voltage issues. And then the pricing challenging like renewables and DER could continuously reduce the marginal cost. How we can provide the efficient price to value the essential reliability need, and then keep resource compensated appropriately. And then so we actually have some ongoing computational research with the National Lab, the PNL, Groovy, and the GE Grid. It's aiming to use explore the high performance computer and parallel computing. So this slides basically summarize some of the area we are researching on, like the first of all the unit commitment optimization model, the tighter formulation. So actually working with several professors, including Professor Jim Ostrowski from UTK, and then also there are some ways, some smart heuristics to take advantage of the problem-specific structure, and then also like symmetry. The Professor Jim Ostrowski has some good research in the symmetry, and then also some like a partition of the problem, and then of course some decomposition method. So those are basically trying to leverage the parallel computing and then break the large problem into small ones. So the goal of this project is really to achieve eventually achieve 10 times speed up. So we're working hard toward that. So I think that's all of my presentation. So sorry for the delay at the beginning. Is there any questions?
Hi, Dr. Chen. Thank you for the presentation. You mentioned that in 2009 you implemented the ancillary services market, and the reserve decreased by about 35%.
Yeah.
What was the main explanation for this decrease?
I think basically for the contingency reserve, it's actually easy to understand. So basically, because normally we prepare for the largest event, right? So in the past, each country area, they will carry their own reserve, prepare for the largest event. But normally you don't have this event happen at the same time, right? So even if you consolidate like at MISO, the contingency event is only happen like once a couple of weeks. The probability is pretty low. So when you have this large region to share the contingency reserve, then we can greatly reduce. And then, but for the regulating reserve, I think part of it is like we're doing 5-minute dispatch. So and also MISO has dedicated resource, for the forecasting group. They have on call, monitor the forecast, and then so with 5-minute dispatch and all these, the dispatch from SCAD is already very close, and then so the regulation is really just bridge the gap, right, between the dispatch and the actual system condition. So that's why we can keep such lower regulating reserve requirement.
Any other questions in the room? I'd like to open it up to our WebEx audience if there's any questions. Hopefully you're unmuted. Any questions from the audience on the WebEx?
I went ahead and PowerPoint calendar. Somebody has a question.
So I hear a lot of echoing. Not sure if anybody captured the question.
Can you ask the question again?
When we were unmuted, I think we got a lot of feedback.
Do you have a question you'd like to ask now? Okay, well, I was just going to say because of the technical difficulty, this is Lisa Beard. If you want to email me your question, I can certainly forward that on to Dr. Chen. And I would like everyone to join me in thanking Dr. Chen for her presentation.
Okay. Thank you very much.
Thank you.